afternoon session. The first speaker this afternoon is Professor Eiji Inoue from RIKEN. The title of the talk is Distortion and Moment Measure of the PSH function over.
Thank you very much for introduction. And well, I'd like to thank the organizers. Well, they're not here maybe. For inviting me. Oh, yeah, for inviting me here. And yeah, I could spend quite good time in Cambridge. Thank you very much. And well, yeah, the title is. I think the title looks something weird. You have never seen this kind of title before. Well, yeah, the main topic is what I call non-archimedean entropy, and what I want to explain today is I found a new formula on non-archimedean entropy using these new notions, distortion and moment measure, and these notions are notions in non-archimedean pluripotential theory, and well, I should say pluripotential theory or over trivially valued field. And by introducing these new notions, I could find a new formula on non-archimedean entropy. But before doing it, I must explain what non-archimedean entropy is, and I must explain the motivation for non-archimedean entropy. So I'd like to review some prior researches. Okay. Well, I did not buy Excel some polarized manifold over a complex field. And as you know, if we consider normal test compression, you can define Donaldson-Futaki invariant of this test compression using intersection number. And it is known this invariant, this number is important as we can use it to define polystability, K polystability and K semistability of the polarized manifold, which is conjectured to be related to the existence of CSK metric. Yeah, I should say K polystability is conjectured to be equivalent to the existence of CSK metric. And K semistability is a non-negativity of the Donaldson-Futaki invariant. And it is important because it is conjectured to form a Zariski. Well, it is conjectured to be a Zariski open condition with respect to the formation of polarized manifold. And yeah, so this is important because Zariski open condition is the importance to form a nice modularized stack. And then we believe that there must exist a good moduli space of these objects. And it is known that there's a good success in Kähler-Einstein case. So, and because there is a good tool, because, well, we can reduce the originally CSK equation is an equation on scalar curvature, but we can, in this, if we consider this cohomology class proportional to the manifold divisor, then we can reduce the equation to the equation on ridge curvature, and we have a for general polarized manifold, we have March functional, but we also have, in Kähler-Einstein case, we also have Ding functional, which has more better continuity property compared to March functional, and we can use it to prove these notions to prove the existence of, well, the equivalence of existence of Kähler-Einstein metric and the K polystability. And it is due to, as you know, Chen-Donaldson-Tian and Boucksom-Jonsson used Ding functional effectively too. So their proofs are quite different, but yeah, they provided a non-Archimedean approach to compound conjecture. And on the K semistability side, we have some MMP technique and well, how can I say? Well, we can use MMP and boundedness results by Bilka and some finite generation results help to study K semistability. And as you know, Bloom-Liu-Shu prove the openness, zero-scale openness of K-semi-stability, K-semi-stable deformation family of one variety. Okay, and I'd like to quickly review what happens for general L. And it is now reduced to the conjecture. YTD conjecture is now reduced to so-called non-archimedean entropy regularization conjecture. It is about stuff in non-archimedean pluripotential theory, and many people contributes to this problem, and these people contributes from analytic side, and Boucksom-Jonsson actually contributes it to from non-archimedean pluripotential theoretic side. And I will explain what non-archimedean entropy regularization conjecture is, but well, yeah, and as for openness side, they are analytic. They are only analytic results, and but yeah, later on for algebraic zero-scale openness. Yeah, they constructed a moduli space of CSK manifold, and Jensen essentially proved some openness of, well, analytic cases. And so, as I'd like to explain what non-archimedean entropy regularization conjecture is, I must explain what entropy is, non-archimedean entropy is, and then it's better to replace it turns out, in view of non-archimedean pluripotential theory, it's better to replace this canonical divisor with relative canonical divisor with relative log canonical divisor. And this is the definition of relative log canonical divisor. And this is convenient because if we compare this with the trivial, the pullback of a canonical bundle from X, then there appears log discrepancy. And here, well, is an irreducible component of the central fiber of test configuration, and VE is some valuation on X associated to the central irreducible component. VE is by definition, well, I think it's order E, and this is a function, rational function on X, and this is we put it back to, and this is a function over X times C, or C star, and we divide it by order of the central fiber. And this is the definition of VE, and it defines a valuation on X, not on Kali X. And by replacing this canonical divisor to log canonical one, we have some log discrepancy term. Well, MNA denotes just replace the canonical divisor with log canonical one, and it's the same term with Donaldson-Futaki invariant. MNA denotes is called as non-archimedean Mabuchi invariant. Okay. Well. Yeah. Okay. And here is the definition of non-archimedean entropy. Non-archimedean entropy of a test configuration is the term appeared in the first term appeared in the Mabuchi invariant, and we can see this invariant as follows. If we introduce the set, well, this reads as base. I use this symbol as this is Berkovich space, and base is B, and well. I introduced the space valuations on some, we consider the sum of valuations of some irreducible subvariety, and I take the summation of all irreducible subvariety. And then it gives some set, and the important thing in this talk is there is a scaling action on this space. And this is because we consider Berkovich analytification of a trivial evaluation. And this is just a scaling of valuation. if you have valuation, then you can scale it by you just take the product. And this structure is essentially used in this talk. And we can, if we introduce some measure on this Berkovich space by putting, well, this is the coefficient, and this is the Dirac mass on Berkovich space, Dirac mass on evaluation. So VE is a point of this space. If we introduce such measure, we call it non-archimedean Monge-Ampere measure. Then we can write this entropy as in this form. So it's the integration of log discrepancy with respect to Monge-Ampere measure. And this is just the change of expression. But this is important as we can extend the domain of non-Archimedean entropy using non-Archimedean pluripotential theory. And what non-Archimedean pluripotential theory is, I want to explain now. We can assign, if you have a test compression, we can assign a function on the Berkovich space by this, in this way. And here, well, log S, log S Kali XL is by definition of minus supremum of lambda, which contains S, and here is the filtration associated to test completion. Well, there in the latter slide there appears the definition of this filtration, so I don't like it now. And I should like, yeah, SV is a local generator of the line bundle around the center of V. Well, sorry, center of VE, VV. And this defines a continuous function. This defines some function on Berkovich space. And I don't define topology yet, but we can define topology on Berkovich space using these functions. I just claimed that we endow this space with the weakest topology, which makes these functions continuous for every test completion. And the fact, well, it turns out this topology coincides with what Berkovich defined. And it is known that this gives a compact household space. And it looks like weird. It's not something you can grasp. Well, it's something like infinitely many here. Something like this. But it's still compact household space. Well, and we can also extend the log discrepancy to this space as a lower semi-continuous function. And since this is, we actually have a greatest LSC extension, so we can, the log discrepancy, extension of log discrepancy to this space is unique. And we can further extend the non-Archimedean Monge-Ampere measure to, well, some good space consisting of functions on this Berkovich space, which can be nicely approximated by these functions. I don't explain the meaning of nicely approximation, but there's some notion established by Boucksom-Jonsson. And the non-Archimedean entropy regularization conjecture concerns the convergence of entropy. Well, for general phi, it conjectures that for general non-Archimedean metric, there exists a sequence of test compressions which converges to the given, which gives a sequence of functions converging to this given phi in the E1 topology, and additionally, entropy also converges. Well, we already know that if this happens, the non-archimedean Monge-Ampere measure converges weakly. But since this low discrepancy is lower semi-continuous, only lower semi-continuous, we only know the lower semi-continuity in general. But this conjecture suspects that there exists such. So it means that we can. It means that the non-Archimedean entropy is the greatest LHC extension with respect to Iwan topology. Okay. Oh well. So I mean that now YTD conjecture is reduced to this problem. Okay. And so, well, as for YTD conjecture is, I think it's already reduced to algebraic geometric problem. So there's nothing to do with differential geometric side. And yeah. So I'm more interested in the K unstable case. So what can we do? The main question of this talk is what can we expect for K unstable polarized manifold? And some naive expectation for this question is there exists a unique test configuration which is optimal in some sense. And to make this question, to make this statement more rigid, we must formulate the meaning of optimal, of course, and we want to understand the geometric property of optimal degeneration also. And what we hope is that there's a way to characterize optimal degeneration by some quantity for test compression. So there must be some quantity for test compression, which is maximized by optimal degeneration. So this would be actually the definition of optimal degeneration. Optimal degeneration is a maximization problem of some quantity, or maximization or minimization problem of some quantity for test compression. And we also hope to show that once you get maximizer of some quantity, well-behaved quantity, we speculate that the central fiber of this optimal degeneration is K-semi-stable. I should say K-semi-stable in some generalized sense. And this generalized sense means, we introduce some K stability for polarized manifold with action. I call here it as polarized dynamics. So it is not a K stability notion only for polarized manifold, but we also take care of action or vector field on polarized manifold. And there's actually such a framework, at least two frameworks related to this idea. And it's a well-known external metric, and it's soliton. And there is a invariant. There's a quantity. We can define some quantity for test compression. Say phi test compression. And we can introduce some quantity for test compression by in this way. I think you already know Mabuchi and then functional Ding invariant, but and this part is actually energy, but this part might be new to you. Well, and so this carries some integration with respect to Duistermaat-Heckman measure, and we cannot express this in terms of intersection of test compression, but instead we can express it using equivariant intersection. So I will explain some basics on equivariant intersection, later. But before doing it, let's see what happens for these quantities. And maybe you haven't seen such quantity before, but it can be related to normalized Donaldson-Futaki invariant, because if we consider normalization, well, here T triangle phi means rescaling, sorry. T triangle phi is T is some positive real number, and we define it as a T phi T inverse T, and it corresponds to the normalized base change. If T is an integer, it corresponds to normalized base change. So if we consider the test compression, non-archimedean metric associated to test compression, and if you take integer here, then it gives normalized base. It is related to normalized base change. Then we can also consider such a rescaling for general positive real number. If you take non-archimedean, if you consider non-archimedean functional, non-archimedean metric. And if we consider the maximization along this rescaling, then you can easily compute this term behaves like this term becomes quadratic on T, and this also. So by completing the square, we can easily see that this gives this equality. And so it says that if the test compression destabilizes the polarized manifold, then it gives some Donaldson-Futaki invariant normalized by some quantity. This term, this denominator is called as L2 norm of test compression. So it is L2 normalized Donaldson-Futaki invariant. Okay. And the well-behaved, by well-behavedness, I mean this property. Well, both of these quantities have these properties. If the quantity is maximized by the trivial test compression, then the polarized manifold is K-semi-stable. And we can go the reverse way. And if there appears some new K-semi-stability notion for polarized dynamics, if the the quantity is maximized some product configuration or vector field, more general irrational vector field, then you can say that this polarized dynamics is relatively K-semi-stable. It's related to the existence of external metric. And if you consider eta, eta is denoted by, in literature, eta is denoted as H. Sorry, I use this notation because H is also used in entropy, so it's confusing. So I just use the related character here. Okay, and if your eta is maximized by product configuration, then your polarized manifold is modified K-semi-stable. And if we can go further, if general normal test configuration maximizes these quantities, then you can say the central fiber is also K-semi-stable in a generalized sense. Okay, so as I write here, these two stability notions are defined for polarized dynamics rather than polarized manifold. So to define this stability notion, we must fix this dynamic vector field from polarized manifold. But it turns out there always exists unique dynamics. Given polarized manifold, there always exists unique dynamics which you should use. I mean, which can be relative K-stable modified or modified K-stable with respect to product configuration.
So in 2 there, the C star action that you have is the one generated by the extreme object.
Yeah, that's right. That's right. That's right. And in the eta case, it's related to soliton vector. And it's already proved that there exists a maximizer for these quantities. And well, as for C and A, we must consider some extension of this quantity. So, well, I mean, we want to extend this quantity to originally it is defined on the space of test concretion, but we want to extend it to the space of non-archimedean metrics because we have some compactness if we extend the space. So we can easily, so it's easier to find the maximizer. And the result is, well, this is something on geodesic ray. We can assign, for if you have a non-archimedean metric, you can assign a geodesic ray of the scalar potentials. And the benefit of using this geodesic ray is that we have compactness theorem for geodesic ray. If you consider time-wise convergence of geodesic ray, we have compactness. Well, but it's not known that if you have some compactness result using only non-archimedean pluripotential theoretic language. So we still need to use some correspondence between non-archimedean metric and well, geodesic rays. And here's the result anyway. If we extend the invariant in some nice way, there always exists some maximizer. Well, here maximal means it corresponds to non-archimedean metric. Not every geodesic ray corresponds to non-archimedean metric, but if you can show that it is maximal, it comes from non-archimedean metric. And this is due to, well, and you can show the maximality once you can prove the finiteness of the slope of Monge functional. And this is due to Chidi. So I like Chidi here. And well, so the final result is there always exists E2 geodesic ray. I should write E2 here. E2 geodesic ray, which maximizes this Calabi, non-archimedean Calabi energy. And in the Fano case, if you consider Fano manifold Fano variety, and if you consider eta invariant or H invariant, then much better is known. Actually, this maximizer can be realized by some algebra geometric object. Well, this is firstly proved by analytic way by Jonsson. And well, I should say they constructed this filtration, and Darvan-Sekirihiri proved that it maximizes this eta invariant. And using MMP, Bloom-Yu-Shujwan proved in purely algebraic way, they proved the existence of this maximizing filtration. And they also, the key thing is the finitely generatedness. And you can observe that if you observe the central fiber of this filtration, okay, this is a slight generalization of test concretion. It's an irrational version of test concretion. And if you can consider central fiber, and if you consider the central fiber, if you see the central fiber is, you can show that it's quantified to semi-stable Q-Fano variety. Okay, I took too much time. Well, this is the result which I really prefer. This relates, well, I already explained the maximization problem of these quantities, but there is some Archimedean side of this story. We have some functional on Kähler metric, whose critical points give extremal metric, precisely extremal metric, and Kähler isolatum. And it is equivalent critical points are actually minimizer. And we have this equality between these quantities. And so if you have a minimizer here, it's extremal metric. And if you have a minimizer of this functional, it's a scalar soliton. And if you don't have minimizer, there doesn't exist scalar soliton, but still we have an optimal destabilizer, which relates any Q-Fun variety to some modified stable Q-Fun variety. And well, yeah, this is just a comment, but this is related to as well. This is of course related to minimization. So if there does not exist extremal metric or Kähler soliton, for instance, then you can consider some flow equation. In this case, you consider Calabi flow, and in this case, you consider Kähler-Rich flow, and you can show that the maximizer here assigns some geodesic ray asymptotic to this flow. Okay. Yeah, I think this is quite beautiful results, and it reminds me of this scenery. So this is Archimedean side, and non-Archimedean optimal degeneration looks like some reflection of Mount Fuji. And yeah, this is we call Sakasa Fuji, and it means upside down Fuji. Yeah, I used to consider optimal degeneration as something like this ideal thing, but recently my feeling is because there always exists optimal degeneration, my feeling is optimal degeneration is actually this one, and canonical metric is something more ideal. Okay, anyway, I'd like to explain what non-Archimedean entropy is. And the first thing I should explain is the Duistermaat-Heckman measure. Duistermaat-Heckman measure is defined as usual, as appeared in Boucksom-Jonsson paper. Well, we can define Duistermaat-Heckman measure of a polarized scheme with GM action by using weight decomposition of the cohomology, and we just take the limit of some measures, sum of Dirac masses on R. So it defines some measure on R, and well, and for general, this is for polarized scheme with GM action. And if you have a test compression, you have a GM action on central fiber, and you can define the Duistermaat-Heckman measure for test compression as the Duistermaat-Heckman measure of the central fiber. And you can compute it using the filtration associated to test compression in this way. And here lambda plus means the well, sum of all f lambda prime, where lambda prime is greater than lambda. And well, and yeah, you might think this is something is slightly different on something you already know. In Boucksom-Jonson's paper, they fix d equal to 1, and it defines some filtration, but this filtration is more related to non-Archimedean metric. So I prefer this definition. Okay. And we can relate Duistermaat-Heckman. We can understand the Duistermaat-Heckman measure as equivariant intersection. So I'd like to explain what equivariant intersection is. It is as intersection is defined. As you know, intersection is defined using cohomology, or if you prefer Chow cohomology, you can use. And equivariant intersection is defined using equivariant cohomology instead. And well, yeah, let us consider a scheme with GM action. Then, well, let's see. Yeah, then we can define GM equivalent cohomology of this scheme by, well, I assume Z pi over C. Then we can consider cohomology, but instead we can use Chow cohomology. But as this is actually, this is a classifying space of GM, so it's actually infinite dimensional object, but this cohomology, well, if we take finite dimensional approximation of this classifying space, this turns into a finite dimensional object, and we can define for sufficiently large n as for sufficiently approximated classifying space, finite dimensional classifying space, this doesn't change. So we can also define these objects even for the field of characteristic E using Chamfer homology. Anyway, and here is an example of calculation. The GM equivariant homology of point may not vanish for P greater than dimension of P. I mean, dimension of P is 0, of course. So the usual homology vanishes for all P, or for all positive P and negative P. But GM equivalent homology may not vanish because from this definition, it's the homology of infinite dimensional projective space, and it gives if you take even P, even non-negative P, then it turns out this is equal to Z. And similarly to the usual homology, we have cup product which for GM equivalent homology, and we can also define GM equivalent push forward. And using this, we define equivariant intersection. Okay, the equivariant intersection is just defined in this way. I firstly explain self-equivariant intersection. First, we pick GM equivalent second homology class, and then we can take L times of cup product. It gives a GM equivalent homology class of degree 2L or Z, and we integrated it. So we take the push forward, then the degree becomes 2L minus n, 2 times of n minus n. And as I said, this may not vanish for L greater than n, L not less than n. So even for L larger than the dimension of Z, it might give some non-trivial number, non-zero number. And we can actually compute this if you pick an ample line bundle with GM action, and if you consider the GM equivalent Chang class of the line bundle, then we can compute the GM equivalent intersection in this way using Duistermaat-Heckman measure. And this is a formula for self-intersection. And well, we can generalize this equivalent intersection for more. Well, we use here we use a function fx equal x L. And we can consider more general f. So if we have a homomorphic function, an entire homomorphic function, which can be expanded in this way, then we can define a GM equivalent f self-equivalent intersection as a summation of these equivalent intersections. And we can easily see that this can be computed. If you pick an ample line bundle, it can be computed by Duistermaat-Heckman measure. Okay, so here's an example of computation. Well, yeah, before explaining this, I must explain the equivariant localization. Well, I explained the equivariant intersection for, okay. If we consider test compression, compact test compression, I should say, and if we consider the first-term class, GM equivalent first-term class of this Q-line bundle, and then we obtain then we can restrict it to the second homology class, second equivalent homology class of the central fiber, and we can compare these equivalent intersections. So this is the equivalent intersection over Kali X, and this is the equivalent intersection over Kali, the central fiber, but this compression. And we can see that if we take the sum of these equivariant intersection, it gives the usual intersection. And it means for, as this is not equivariant intersection, for L not equal to n, it just gives 0. So it means that this coincides with minus of this, except for L equal n. And if we compute, as you know, well, this is the energy term in Donaldson-Futaki invariant, and we can compute by equivariant localization. This is equal to minus sign of equivariant intersection on central fiber, and by the last formula, by this formula, we can compute it in this way. Recall that the Duistermaat-Heckman measure is associated to the GM action on the central fiber rather than the total space. So we must use a localization formula. A localization formula is essentially Stokes theory. And we can also compute the more higher equivariant intersection. And if we substitute n plus 2 here, then it turns out this can be this gives the integration of quadratic with respect to this Duistermaat-Heckman measure. And if we can also, because the exponential is a entire homomorphic function, we can consider equivariant intersection of exponential equivariant intersection, and then it can be computed in this way. And here appears this term because of this. Okay. And we can also consider twist. Well, maybe I should go fast. Well, anyway, we can define GM not only self-equivariant intersection, we can also define such equivariant intersection if we pick two equivariant homology class. But it's important to understand the equivariant intersection for not coming from homology class, because we want to substitute a canonical divisor here, and canonical divisor is not necessarily completed. So instead of using homology class, we can use Borel-Moore GM equivalent homology, and then canonical divisor lives here. So anyway, we can define equivariant intersection of canonical divisor with L. Okay, here's the definition of non-archimedean entropy. Well, this and this is the usual intersection, and here appears equivariant intersection. You can compute this term as the integration of exponential with respect to this Duistermaat-Heckman measure. But this is more complicated. We consider equivariant intersection with log canonical divisor. And it turns out, well, this has this is well-behaved quantity in the sense I explained in the context of the well, CNA and H entropy, H invariant, sorry. And this is a result if you consider normal test configuration which maximizes non-archimedean entropy, then its central fiber is mu-K stable. Actually, we can generalize the result to finitely generated filtration. So I write here double non-Pascal. And well, let's see. And here a new notion appears, mu-K semistability. Mu-K semistability is related to some generalization of CSCK metric. It's some kind of a canonical metric which I call mu-CSCK metric, which comes up from generalization of the notion of Kähler soliton to general polarization. And I like here which it unifies is the framework of extreme metric and Kähler soliton. But here I only explained well, some special case of non-archimedean mu entropy. So and there's a extra parameter in the framework of mu-C-secant metric. And if you introduce the parameter, you can relate the mu-C-secant metric with the extremal metric and calculate solution. But today, for simplicity, just for simplicity, I'd like to explain non-parameterized version. Okay. And the non-archimedean as Calabi, non-archimedean Calabi and the Calabi functional related, non-archimedean entropy is related to Perelman entropy. And the Perelman entropy is defined something like this. And usually there appears parameter here, but today I just put lambda equals to 0. And then we can consider some functional Kähler metric, which is called Perelman mu entropy. And I can show some inequality between non-archimedean mu entropy and Perelman mu entropy. And the proof is similar to exactly the same as what Carlo explained. So we prove some monotonicity of Darwin entropy along geodesic ray, and we show that the limit gives invariant. And so equivariant intersection formula helps to prove this equality. Okay, so of course I conjecture that equality holds. But if you introduce parameter, this equality, my speculation is this equality is true only for non-positive lambda. But in final case, some miracle happens that in final case we take lambda as 2 pi, and then some miracle happens, and I already know the equality holds in final case. As this is a conjecture for general polarized manifold.
Is there any counterexample for positive case?
Positive, well, I don't know, but some, yeah, non-negative, non-positive case is well behaved. Well, because essentially because, well, let's see. In the non-negative, in non-positive case, we can show there exists a unique maximizer for this double entropy. Then we can apply, let's see. Yeah, the uniqueness is, my feeling is uniqueness is important to the equality. I don't know a counterexample, but my speculation is something like that. Okay, here appears Sakasafuja again. Okay, so in last 10 minutes, well, I want to explain what distortion and moment measure is, but before explaining it, I'd like to show the application of these notions to non-archimedean entropy. The first thing is that I found a new formula of non-archimedean entropy, and even for H and invariant, we have some new formula. What I did is I introduced some math from the space of test compressions. I can actually extend this domain to the space of non-archimedean metric, but let's say, let's consider the space of test compressions. And I consider the map from the space of test compression to some certain nice the space of non-archimedean metrics, such that this formula holds. And originally, this non-archimedean entropy is defined in terms of equivariant intersection of test compression. But this is, as you know, this energy, well, I didn't explain what energy is. ENA is just ENA of test compression is just some coefficients, and we take the intersection. So it's defined by a usual intersection, and distortion helps to relate equivariant intersection to the usual intersection. So we can reduce things to usual intersection by introducing distortion. And well, later I explain distortion, what distortion is, and the property. Well, and I can show that the energy. Well, we have this equality, and this is always negative because this is positive, and here is minus sign. So maximizing this quantity corresponds to minimizing Mabuchi invariant. Some certain normalized Mabuchi invariant. Okay, this is the first result, and using this, we can actually show the existence of optimal destabilizer for mu entropy. But we must replace non-archimedean Mabuchi with the Mabuchi of slope of Mabuchi because we still don't know if the entropy regularization conjecture holds. If we can show the entropy regularization conjecture, we can show this equality. The equality holds, and but we still don't know. So I replace this with the slope of Mabuchi, and then we can apply some entropy compactness theorem to prove the existence of optimal destabilizer. So I use some geodesic ray convergence. Well, let's see. Yeah, so as I write here, if the non-archimedean entropy regularization conjecture is true, this theorem means that there exists a maximizer for non-archimedean mu entropy. But this is slightly, what I proved the existence of maximizer is for slightly different functional so far, but I believe it's true. Okay, and here's some, here's some corollary. Yeah, in view of this conjecture, I suspect this is true. And if this is true, we can show that mu CCK metrics are unique modulo of the automorphism group. And this corresponds to the uniqueness of, in the theory of Keller soliton, this corresponds to showing the uniqueness of soliton vector in Tianju's theory. Well, I mean, using Tianju's functional, we can show the uniqueness of vector which may admit a Keller soliton, but in the mu CSCK framework, they are not convex. So it turns out the problem becomes much more difficult. But it turns out, well, let's see. If we connect, if you connect two non-archimedean metric by geodesic, then this is not, let's write phi t, then this is not convex along t. But as we have this formula, as we have this formula, this phi and this phi, let's see, and we already know, we can see that, let's replace this with slope of Mabuchi, then we can see that this is convex along with geodesic connecting two. So we must consider, instead of considering this kind of path, we must consider some geodesic ray connecting this phi 0 and this phi 1. And I can show this can be written as this phi tilde t for some phi tilde t. But this is not a geodesic. This is geodesic. And then I can show some convexity, and it proves the uniqueness. And I can also show that the case semi-stability is actually equivalent to maximization of non-archimedean mu entropy. Okay, well, here's the definition of distortion. I only have 5 minutes. It's quite simple. Well, this is just a review. Well, let's consider a function on Berkovich space. And and consider some increasing concave function on R. Then we can introduce a chi distortion of phi by defining it as this function on Berkovich space. Define the function on Berkovich space, and it turns out this gives a here this chi block triangle means the Legendre transform of chi gives chi, and it turns out that this chi is if the original metric if the original function is non-archimedean PSH, then this phi also gives an non-archimedean PSH metric. And we can see it's good to see toric. It's good to see this object in toric geometry. It corresponds to the in the Legendre transformation side. It corresponds to the composition of convex function, concave function maybe. Well, concave function is this concave function, but this is a function, concave function on moment polytope, and the non-archimedean metric is the Legendre transform of this convex function. So we first take Legendre transform and compose it with chi, and then going back by Legendre transformation. And this chi phi is something corresponding to this. It's not the same as composition, but it's the conjugate of composition. And we can express this non-archimedean distortion in terms of filtration. In terms of filtration, it's just if you have a filtration, then we can define, we can easily show that this filtration associated to distortion is equal to the, we just changed this term, by chi, using chi. For instance, if we, in the framework of mu-C metric, we use this increasing concave function, and the computation is something like this. Here, log of this. Okay. Well, and we can easily show that this is a distortion of Duistermaat-Heckman measure. Well, yeah. There is, as Min-Chen explained, there is a way to extend the Duistermaat-Heckman measure to the space of non-archimedean metrics, and we can easily relate this Duistermaat-Heckman measure of distortion with the original Duistermaat-Heckman measure. So it's the push forward by chi. And then, and we can easily compute using this. We can compare the distortion of this integration. Let's see. We can compute the integration of this for distortion, and can be written by the integration of some function related to chi with respect to the original metric. And for being invariant, we want to compare this part, which is the Legendre transform of non-archimedean entropy, and we can easily compute. We just commute infimum, and then the result, distortion of LNA, can be computed as in this way. But Mabuchi invariant behaves quite differently. Well, so this proves the this fast equality. And let's see. Yeah, but I don't have time. But as I explained, non-archimedean entropy is concerned with equivariant intersection with the relative low canonical divisor, and this term is much more difficult compared using distortion. Similarly to Chen-Tian formula, we can decompose this equivariant intersection into something like this. Here appears log discrepancy, but here appears some integration of exponential with respect to Duistermaat-Heckman measure. And here appears Duistermaat-Heckman measure of each reducible component. And I want to interpret this part and by introducing something I call moment measure. It's a measure. By introducing this measure, we can compare equivariant intersection and appearing in Mabuchi and the usual intersection. Well, here's the definition. And this, if you consider push forward, this is a measure on the product of Berkovich space and the R. And if you consider push forward this measure to Berkovich space, then it gives non-archimedean Monge-Ampere measure. And if you consider the push forward this measure to R, then it gives a Duistermaat-Heckman measure of this test compression. So it's a mixture of Monge-Ampere measure and Duistermaat-Heckman measure. And I can show that we can extend this functional to space of non-archimedean PSH metric continuously. And what I want to explain is this equality. Well, what I realized is the moment measure of distortion can be computed as the push forward of original moment measure. And here is the definition of delta chi. It is a map from the product of Berkovich space to R to the product of the same space. And it's defined as in this way, where chi dot denotes the right differential of concave function. And then from this theorem, from this formula, we can compute. Well, this is what the term appearing in non-archimedean entropy. This is nothing but this term, and we can compute it using this. Since this is using Fubini theorem, we can compare it with this. And since this logo discrepancy is homogeneous, we can put this kind of here. And then this turns out to be the integration of pullback of logo discrepancy with respect to this map, and it turns out this is the integration of logo discrepancy with respect to push forward of moment measure, and it turns out that from this formula is the integration with respect to distortion. But now this is a function on this doesn't have variable on now, so it is an integration on x space. So as I said, the push forward of this measure to Berkovich space gives non-archimedean Monge-Ampere measure, so we can reduce things to non-archimedean Monge-Ampere measure. Okay, that's all. Well, here is lot of questions, but that's all. Thank you.
Thank you so much. Is there any question or comment?
So is there an Archimedean version of this distortion operation?
Yeah, I'm thinking of it. Well, if you can find nice things, then I think we can prove the, well, at least I think we can prove this inequality here. This inequality here. Well, yeah, I think so. Well, this inequality is still non-trivial because I consider not only test compression but also general non-kinetic.
And so you take a test configuration and you just get something back in E1? I mean, do you have examples where you really don't get something that's test configuration?
Sorry, what?
I'm just asking about the regularity of the distortion.
Regularity, yeah. Regularity is, I have a question here on regularity. Yeah, my speculation is, in general, there is no test configuration which maximizes non-archimedean entropy. But my speculation is it assigns some filtration. And at least I speculate it can be RIKEN. Oh, sorry, this is I should write cap. it can be written in this way, like divisorial filtration. But here, I speculate BI valuation is only cosmonomial. This is my speculation, but still we cannot realize this object as a geometric object. But my speculation is there will be a theory extending the theory of scheme, which by which we can understand this object as some kind of space.
Is there any other comments?
So can you fit your picture into what shall we talk about on Monday? The automorphism of the optimal degeneration has decomposed into some reductive.
Yeah. Sorry. And your question is?
I'm asking whether it's possible to fit that into your picture.
Yeah, that's a good question. I don't know, but yeah, Xiaowei tells me that there might be some extension of his theory, which explains my framework. But it's a good question, but I don't know. So.
Is there any comment? If not, let's thank the speaker again.